Hi, my name is Luka Crnkovic-Friis and I'm the CEO of Peltarion. And we're the makers of a platform that makes cutting-edge AI available for all, not just the Googles and Microsofts of the world. Now, we have customers that range from very tiny seed-stage startups to industrial giants that have been around for, centuries in some cases. Now, both ends of the spectrum are very interesting for different reasons. The startups for their raw energy and fresh ideas, and the larger enterprises for their ability to make a really massive impact. When an enterprise really decides to do something, big things can happen. So in this video, I'll be focusing on enterprise and the road to becoming AI first. I want to share what we've learned, what works, and some of the things that don't work. At the core of what we do is the question of what happens when you radically reduce the cost of deploying cutting-edge AI. We believe that will truly change the world and advance humankind, as AI will be able to supercharge basically every part of life and business. Our way of doing that is through our platform that allows non-AI experts to build and deploy real-world AI systems. Our Peltarion has more than 15 years of experience of working with AI in industry, and we've had customers such as NASA and Tesla. We have a very broad experience of what goes right and what goes wrong when you try to apply AI at large scale. Now, almost every enterprise today has some sort of digitalization strategy or policy, and usually AI is part of that. But most are finding it rather difficult to scale. And there are a couple of reasons for this. But one of the core things is that there is a misconception of that AI on one hand and analytics and big data on the other hand are the same thing. But they're not. Analytics and big data is all about centralizing your data. You get it through a data science department that analyzes the data, and you get some sort of actionable intelligence out. So you get some information that you can act upon and do that can improve your business. This is a super important thing to do. Every company should be doing it. But it's also a majorly expensive and difficult thing to do. Just if you're thinking of an enterprise that's been around for a while, the concept of just getting the data accessible in one place and standardizing it, it's a lot of work. And I know of no enterprise that hasn't spent many millions and many years getting to that stage. It's super important, but also super expensive. The output you get is intelligence. You get something that you can act on and improve your business. And the key people here are the data scientists. Now, AI on the other hand, you don't really get any type of understanding or intelligence from it. What you get is a solution. It's an engineering tool. It solves a problem. What you get out is a solution to some problem. You don't necessarily get any wiser on why it works, how it works, and so on. But it can help reduce costs, it can help create new business opportunities, and so on. But the most important differentiator is that unlike analytics, which has to be centralized, and where the data scientists are the key, for AI to work, it has to be decentralized, and it is the domain experts that are the key. Now, imagine that you have an antenna designer at some company that produces mobile phones. Now, you have an engineer there who's been working 30 years with antennas, specialized in antennas. The idea that a junior data scientist from a central data science department would come and say, "Oh, we're working with antennas. How nice. Would you like some AI to that?" That's the concept. It won't work. The domain knowledge about the antennas is far more deep and far more complex than the AI bit. And it's not fair to the poor data scientists either, because one second they have to do financial forecasts and the next second they have to start thinking about antenna design. So the only way AI is scalable within a company is by distributing it and get it into the hands of the domain experts. And the good thing is that since it's decentralized, you don't have to do this big data centralization thing. The data question can be solved locally, meaning that AI projects are potentially much, much more affordable than these large-scale analytics problems. Generally, a combination of central strategy and distributed execution is necessary. Now, we usually refer to the fundamentals as the 3 pillars of enablement, and this is pretty much a pattern that goes for all companies that we've encountered. Now, the first one is tools and talent. So you have to have need the right tools for the job, and you need the right people to execute it. Okay? The second bit is behavior and mindset. Now, you can have 2 companies that operate in the same vertical that have basically nothing in common when it comes to technology adoption, and their behavior will be very different. And to start thinking data-driven, to start thinking AI, the mindset needs to adapt. You sort of have to integrate it into the behavior and the way of the organization thinks about things. And the third pillar is process and organization. Sort of how do you arrange everything, how do you organize everything. Now, the first pillar is basically common for just about any business, but the other 2 are highly dependent on the individual company. So what I want to do in this video is to go through the tools and talents first, which is the general part, and then numbers 2 and 3, which I call the other stuff. I'll give a couple of use cases that shows different types of companies and different types of use cases and different types of approaches. But there are today 2 major obstacles for businesses of becoming AI first. Now, the first thing is that it's really difficult to find people who know AI. Where do you start? You can get data scientists, but they are very expensive and hard to find. You can forget about AI experts unless you're Google and Microsoft or one of those guys. They'll very likely be way outside of your budget or even ability to attract. So data scientists are, they're hard to find, and the situation is not getting better over time. The second bit, that a lot of this cutting-edge AI technology has not been designed for actual production use, but it's been built for research, for academic research by academics. And the only way forward to actually put a system in production is to use a patchwork of different technologies. Now, usually when people talk about AI and how they think it works is that you get some data, you pre-process it, clean it up, build your model, train it, and if it's good enough, analyze it, and you're happy. If it's not, you iterate a bit on it. And this is fine. This works if you're doing a proof of concept. This works if your point is writing a research paper. But if you actually want a industrial grade or enterprise grade production system, this isn't the reality. The reality is far more complex. You have to version control your data. These AI systems run on exotic hardware that you have to manage. You have to have monitoring in place, serving infrastructure, and so on. So there's a lot of stuff around. It has to be built. And the way that many attempt to do this is by using a patchwork of different combination of open source tools, closed source tools, and try to get them to work together. There are 2 problems with that. One is that first, it requires a lot of expertise. Not just data scientists, but you need data engineers, you need production engineers, and so on. So you need multiple groups of experts working together to get it to work. The second bit is that the different parts in this puzzle have not been designed to work together. In fact, this field is developing so rapidly that very often these tools that you're trying to combine are on different trajectories and going in different direction, which means that maintenance over time becomes super hard. All of this comes down to that it's expensive to do this. And because it's expensive, you can't do it in every department. You can do one of these one-off projects if you have a data science department and you invest a lot of people and money in it, then it's doable. But then again, you end up with a scaling problem. You really can't get it out into the organization. And this is where Peltarion comes in. So it's one platform that takes care of the entire pipeline. Now, of course, it doesn't do all of the things that each of the individual tools do, but it does all that it's needed for deep learning, and it does it in such a way that it's, one, possible for non-AI experts to use it, and number two, that you can actually put stuff into production and rely upon it. Which brings us to the point of what AI should be. Well, you should be able to connect some data easily. You should be able to see the data, inspect it, and get help with any pre-processing. You should get help building the model, training it, and if it's not good enough, help iterating on it. And when you're done, click a button and have it in production. Now that's the theory anyway. So let me start by doing a demo. The first step is to log into the platform. We're going to start by creating a new project. Call it Platform Demo Video. Now, we have a variety of ways of getting data in, which is the first step. We can connect to an external database such as BigQuery or Azure Synapse, or we can use the Data API to programmatically get data in, or simply type a URL or drag-drop a data file. Or in this case, what we're going to do is we're going to use the built-in data library, which consists of a bunch of free datasets. Now, for the first problem we want to solve on the platform, let's take something that's very typical deep learning, like image classification. Here's a flower dataset that we're going to load. Now here in the dataset view, you can pre-process, preview your data, and modify it in various ways. It has two modes, a simple and an advanced. In the advanced mode, you can do all sorts of manual changes and additional pre-processing, handle training set, validation sets, and lots of complex stuff. But for this demo, we're just going to stick to the simple mode. Now, as you can see, the data consists of a bunch of images of different flowers, and there's a label that says what flower it is. So what we want to do is we want to build a neural network that's going to predict what flower it is from an image of the flower. So we click on Create Project, and let's call this Flowers. Click on Next. Here we are asked to select inputs and targets, meaning what is our input data, the image, and what is the target, the name of the flower. It will be selected automatically for us, so we don't really have to do anything here, but click Next. And here it's going to suggest problem type. In this case, it's single label image classification, which is correct, so let's click Next. Now we are in the modeling view. This is your neural network. Now, we can just press play to run, but if you want to do something more advanced or even build a network from scratch, you are by no means limited to the stuff that the wizard produces. You can just add new blocks and connect them and build whatever custom model you want. But we're going to delete this and go back to the model that the wizard created and just press run. What you see here is the evaluation view. Here we can evaluate the experiments that we built, see the performance of the models, compare them, and see how well they are doing on validation and test data sets. Here we can see now the system is training, and we'll see over time performance as it increases. In this case it has been sped up, so we don't have to wait 10-15 minutes for it to complete. Now after one epoch, meaning that it's seen the data once, we can actually start and look at the results. We go into prediction inspections. Here you have a confusion matrix. Confusion matrix is a way of visualizing of how well a classification algorithm works. Now, if it was perfect, then on the diagonal, everything would be 100%. That would mean that every single classification it did was correct. Now, this is very good, but not perfect. And we can see that it makes some mistakes, and we can actually inspect and look closer at those mistakes. For instance, here, how it confuses, on occasion, tulips and roses. And we can see those examples. Now, while we've been looking at this, it's been continuing to train in the background. It has probably come a bit further, so we may have some new data to look at. See, drop down here, and here we can see, yes, there is one new epoch. Look at it, and this is much better. In fact, this is so good that we can actually pause the experiment here, and then move on to the next step, which is actually deploying the system. So we click on Create New Deployment, and just click Create. And this is the deployment view. Here you can see and manage all of your deployments in your project. You can create new ones, enable them, disable them, and get all the information you need to connect it to an external application. You also have the link to the API tester here, which is a simple app to test your new APIs. We enable the experiment, and then we click on the API tester. Now, the API tester is a very simple web application which allows you to test an API, meaning the model that you've just built. It allows you very simply to, like in this case, to drag drop an image and get the result. Here we see a tulip, and it's a tulip. Nice. Let's see another picture. This looks like a sunflower. Yes, sunflowers, so this is correct. That is how simple it is to build your first deep learning model. Now let's move on to a second example. We'll still stick to images, and let's do an image similarity model. We go again to the dataset library, and we scroll down and choose the groceries dataset, which consists of a bunch of images of different groceries, like milk cartons, like different types of vegetables and fruits and so on. Stuff that you might find at a grocery store. And it also consists of, has labels to that. So an image plus label. We're going to create a new experiment, call it groceries. Click on next. And in this case, we just click on next here as well. We have the image as input, that's nice. And we select image similarity as our task and click next. So here we have the model. In this case, we'll just press play. And again, here we see the training. It has been sped up. It actually takes 10 or 15 minutes or so. And when it's done, we can simply create new deployment. And we'll click on similarity search and click on create. Now it's going to build its image index, meaning that all of the data that we've uploaded is going to get indexed so that the search can be performed. This is a relatively slow process, so we're just going to speed that up and come back when it's done. Now it's done. So, next step is to enable deployment, and we can again try it out with the API tester. So we take an image, in this case of a milk carton, and drag drop it, right? And look at that, we have other cartons. And what's interesting, if you observe the results, you can see that those are all cartons, but they are of different colors. It's a fairly advanced search that really understands the content of the images rather than the sort of superficial things such as colors or shapes and things like that. Now let's take a second one, some peppers. Yeah, that worked really well as well. So that was image similarity. Now let's move on to text instead. We're gonna again pick a dataset from our data library, and this is the Internet Movie Database dataset that consists of a bunch of movie reviews and an associated sentiment, meaning that for each review it says, was it a positive review or a negative review? What we want to do is to build a model that takes text as input and then tells us if the sentiment is positive or negative. Do it in the same way. Create new experiment, call it IMDb, click on next, the inputs review, that's correct, binary text classification, correct, firm, and here is our model. And it suggests a multilingual BERT, which is great, meaning that our model, even though we only train it on English data, it's actually going to support 100+ languages. And we press play to train. This is one of those models that take quite a bit of time to train. In fact, now we're back. We can see how long it took by switching here from epochs to elapsed time, and we can see that it took about 40 minutes to train. So this is one of the slower models that you can find. Again, prediction inspection gives us an analysis of how well we're doing and can look into examples where things are not working as they should. And when we're sort of happy with results, we create new deployment and click on create, enable it, and we can again just test it in the API tester. Now let's start with something simple, like this is good. Sentiment true, so it's positive. This is bad, sentiment negative. Well, let's try something a bit more advanced. Something that would confuse regular sentiment analysis algorithms, but that neural nets can actually do really well. So we'll write something like, somebody could think this was good, and it recognizes it as a negative sentiment, even though it contains the word good. So it really understands the semantic meaning of the text. And of course, as I mentioned, it's multilingual. This is in Swedish. I love this. Sentiment true. Or somebody could think this was good, but in English. But in Swedish. Sentiment false. Alright, let's take a different dataset. And let's do, instead of just using the data library, let's actually upload a dataset. So I have this CSV file containing a lot of hotel reviews of a certain hotel, of Grand Hotel in Stockholm. Now the fun thing about this dataset is that it consists of more than 40 different languages. And what we want to do is build a text similarity model so that we input some text and it finds us similar reviews. And you can see here it consists of a bunch of different languages. I'll create new experiment. Next. Now we don't want the title as input, we actually want review as input. And the target doesn't matter since we're doing a similarity search. We'll select text similarity, click create. Now what we can see here is that it created a model that is called a universal sentence encoder. And this is a nice model because it's fast and it's simple. So it's very quick to train and it executes really quickly. But it only supports 16 languages and is relatively primitive. So what we want to do is, and this goes into the more advanced territory now, we want to exchange this model for an XLMR, which is state-of-the-art, a really advanced model that supports over 100 languages. Now we do that by removing the universal sentence encoder. We add the XLMR by clicking on it, and then we reconnect the blocks here. And that's it. And then just press play. Again, sped up training. And we create a new deployment. Select similarity. create, and then the index is created, and clicked on enable and try it out. And then we start with something like the restaurant was great. As we can see, the results are very similar in meaning, but not in exact words. It talks about great food and so on, and doesn't specifically mention a restaurant. Let's try something different. In Swedish, luftkonditioneringen fungerade inte, means the air conditioning didn't work. And query. As we can see, it gets it. It talks about air conditioners, about being too hot in the room, and so on. So it understands text on a semantic level. This is a super useful method for searching text, not based on keywords, but based on their actual meaning. Finally, we're going to look at something completely different, tabular data. Now let's go into Google Sheets, and here is a data set that contains bid pricing. So basically it's from an auctioning site, and it consists of a bunch of items, what the retail price is, and then what their bid price is. And the data set consists of a number of variables, features, item number, retail price, which category, and the number of sellers, the color of the item, the winning bid price. As we can also see that this is not a clean data set. There's missing data in it in all sorts of places. And we look at the 2021 data. It looks the same, except of course the bid column is mostly empty because that data hasn't come in. Now what we want to do is build a model that will forecast, that will predict the bid based on the other numbers, so we can fill it out. So we go back to 2020 and we download the CSV file. Then we switch to the platform and drag drop the data and call it bid prediction. And you get a pop-up here saying that the data had errors in it, but they have been fixed. And you can actually look at the stuff that has been fixed and what it has done. Here's the data set, and you can see all of our variables here. And let's create new experiment. Well, bid prediction. Click on next. And now we will select inputs and targets, and input should be everything except bid, and what we're predicting should be bid. Click on next. Tabular regressions right. Click on there, and there is our model. We can just click play to run. This trains actually really fast, so we don't have to fast forward. We can just do this in real time. Let's look after one epoch, sort of how well we are doing. Pretty good. It's still a bit banana shaped. Ideally that would be a line if the prediction was perfect. We're just gonna let it train for a little bit more and go back and sort of select the latest best epoch. Look at it and see if it's a bit more linear than the last one. And yeah, that looks fantastic. So let's press pause here and just create new deployment. And just enable it. Here we have our variables. And then copy the URL here. Go back to Sheets. Activate the Peltarion plugin. There's one for Excel as well. Click on Enter Credentials and paste the URL that we copied. Go back to the platform and copy the token. Go. Paste it here and click Connect. And now it's connecting to the platform, and this will allow us to call the model that we built and deployed from within Google Sheets. It's pretty cool. There we go. First step is to select the header range, which is basically our input headers. Here we go. And click there. Then it's asking us for our data inputs, which is where the data is, input data. And that's going to be all of this. There. And then it's going to ask us for the output. Now we could select this here just to get where we actually have values that we can check, but in fact we're going to just select everything here because we want values all the way. There we go. And now just click on predict. And there we go. Actually, this isn't too bad. It's pretty close. Pretty close. So this was a fairly good model. Yeah, that's pretty good. And here we have the values that haven't been before. Nice. So that was a brief view of the Peltarion platform. As you could see, it was very simple to solve a variety of different types of problems using both unstructured data such as images and text, but also structured data such as tabular. And of course, you can combine all of those so that you have a combination of tabular and images, for instance. Now, just to give a perspective on what you've seen, we've set up a little competition between the Peltarion platform and Amazon's flagship deep learning platform, Sagemaker. Now, Google and Microsoft have very similar offerings, so it won't be a big difference. Competing on the Sagemaker side, we have Mikael, who's a principal data scientist and co-founder of Codon, PhD in machine learning. And on the Peltarion side, we have Carl, who's a mechanical engineer by education, works as a tech writer, so he's not a data scientist, and he's the head of knowledge center here at Peltarion. Now, the problem they have been tasked to solve is building a custom model that classifies car damage. Now, the data consists of some images of the damage and some tabular data, like the manufacturing year of the car. So it's a multimodal problem, both combination of images and tabular data. On the left side, you'll see Sagemaker, and on the right side, Peltarion. Here at 5 minutes and 25 seconds, we're done at Peltarion. So after over an hour of trying to solve it on Sagemaker, he gave up. It kept crashing, and it was a problem of getting both the tabular and image data working together. It's supposed to be able to handle it, but he didn't manage to get it to work. Now on the Peltarion side, it was done in 5 minutes. So we decided to simplify the problem and just do an image classification, so remove the tabular data. So given an image of a car, tell which kind of damage it is. This is very straightforward deep learning. Any deep learning platform can do this. Again, on the left side you see Amazon, on the right side you see Peltarion. And they were allowed to reuse their old work. Here in 1 minute 58 seconds, we're done at Peltarion. And this time he got it to work on Amazon Sagemaker. So here we're done. And Amazon took about 53 minutes and Peltarion took slightly less than 2 minutes. Now the big thing is that when you're going to solve the next problem, Peltarion is going to take 2 minutes and Amazon is going to take 50 minutes again. But more important than that, on the Sagemaker side, you'll have just tons of spaghetti code because this wasn't made for actual production at scale. You'll have bugs, you'll have very difficulty actually making use of it. While on the Peltarion side, you're basically ready to go. Alright, that was the tools. Now let's move on to use cases. Now, what is a successful use case? So what are the key elements of a successful use case? The first one, there has to be business value. There are so many AI projects that are started that are just based on, oh, this is a cool technology. We can do this with AI, so let's do it. And those are guaranteed to fail. Unless there is actual business value, don't do it. When you're getting started, it's always good to start something that can be understood at multiple levels in the company. So, something that has business value and that's easily understood. So don't go just for technical goals, but also have very well-defined commercial goals and success criteria. The key number 2 is data. You have to have data. There's no way of getting around it. There has to be a way to get data or that you have it. And the effort of getting the data must correlate to the business value. So there's no point in doing something that costs a lot to get the data, a lot of effort to solve a minor problem. So they have to balance. The third point is there has to be reasonable logistics around deployment. If it requires supporting infrastructure, that infrastructure needs to be in place. Otherwise, there's a really big risk of nothing happening. The AI can't live in a vacuum. One of my favorite real-world examples comes from a company that built this really nice proof of concept of AI interpreting drone images to count the number of trees on the ground. It never went beyond a proof of concept because once they realized that maintaining a massive fleet of drones was not something they were ready to do, it basically died out. One of the key things is that when you start with this process is to commit to deploy, meaning that you start the use case with a clear intention of actually making something that goes into production. Otherwise, there's a big risk that you'll end up with just doing endless proof of concepts that don't lead to any value. The fourth point is try to maximize the probability of success. So start with low-hanging fruit. It has to be fruit, but try with things that have previously been proven to work, especially if the business case isn't super strong. Save the more experimental stuff for later stages. Also, domain expert involvement in the process is critical. It is the strongest predictor if a use case will be successful or not. Don't include domain experts and you will fail. Include domain experts and you have a good chance of succeeding. It's that simple. Thank you for watching. Deep learning AI is the most advanced technology known to humankind. We have been working hard for the last 4 years on the vision of making it usable and affordable for all. And we're very proud of what we have accomplished. If you're interested to try it out, go to peltarion.com and sign up for a free account. Thank you.